Without further ado.
Cool. Thank you.
If you haven't signed in, please sign in before you leave. Remember, that's how we justify our existence.
Excellent. Well, it is nice to be here presenting 2 times, one semester. First one kind of a teaser, second one a little bit more of the details. But as this title sort of indicates, I'm going to be talking about how you can reduce database sizes to be able to facilitate some previously computationally intensive analytical techniques in metagenomics. So the basic idea for this talk is I'm going to briefly talk about what I mean by metagenomic classification. And then we're going to move on to the actual computational technique, which is this thing called Containment MinHash. And after that, I'm going to talk about how you can use this technique over a bunch of different resolutions, from very fine resolution to very coarse-grained resolution. That is going to be streaming multiple k-mer sizes. And then lastly, I'm going to relate it to the average nucleotide identity. So it's going to take this sort of conceptual quantity called Containment MinHash and relate it to something that we all know about. So starting at the beginning, metagenomic classification. So I don't need to tell you guys this, but just so we're on the same page, what is the data? I'm going to be talking about whole genome shotgun metagenomic data. So quick 5-second overview. We have some sort of environmental sample, and people who are much more talented in wet lab stuff than me are able to extract all the DNA, put it on one of these sequencers. We shred, with a machine, shreds all the genomes floating around in the sample, and off comes all of our ACs, T's, and G's, and they're rather large files for whole genome shotgun. So that's the data. We're familiar with this. You might be used to working with 16S or ITS kinds of data. Well, that's very interesting. I do dabble in that. This talk is going to be all about WGS data. I should note, pause briefly, if there are any questions anytime throughout the talk, please pause, just ask away. So now we've got all this data, these reads floating around here. What can we do with them? Some of the very first things you might want to do with a whole genome shotgun metagenomic data is taxonomic profiling. This would be like a step 0. You just want to ask the question, who is present and at what relative abundance? So you want to be able to assign to each taxa some relative abundance of that taxa in the sample, maybe at a certain taxonomic rank. Other things that you could do, and this is much more computationally difficult, is try to assemble these short reads into contigs. Using these contigs, then it's easier to get more information about it because these reads are shorter while these contigs are longer. So you might be trying to assemble genomes or something like that, or you could just want to bin these things. So genome binning in this case is trying to group the contigs into bins where hopefully all the contigs in a bin belong to the same organism, hopefully. Another thing you can do is taxonomic binning, where instead of individual organisms, you try to group them by taxonomic label as well. And there are a bunch of other techniques all around this that, for instance, try to go straight from reads to the taxonomic binnings. So you try to assign taxa labels to individual reads. If you're familiar with things like Kraken, Clark, Bracken, even Metaflan, try to do things like this. Or you might try to bin these directly, which is very, very, very difficult to try to group all the reads together and say all these reads can't come from the same organism. So what we're going to be talking about today is mainly everything besides assembly. So the technique that I'll present in the end is going to give you a taxonomic profile, but it can also be used to do binning either taxonomic or a genome.
That's a good question.
Absolutely.
So this is based, like the binning is based on what the data are available for assigning those taxonomic groups. Is that correct, or is it?
This part, yes. Yeah, this part you don't actually, you might use a reference, but you can also try to do this de novo.
Okay. And so having whole genome sequences of type strains within a given taxa is really valuable for the one on the right, potentially for the one on the left.
Yeah, yeah, exactly. Excellent.
Thank you.
Yeah. Okay, so what do things look like right now for the different sort of computational methods to try to accomplish all these different tasks? So I'm involved with the critical assessment of metagenome interpretation, these sort of big benchmarking kinds of things. And I'm briefly going to review sort of the lessons that we've learned. So first off, oh yeah, reference if you want it. Why is it flashing that little thing? Do you see that whenever I move? That's weird. Okay, hopefully nobody's epileptic. Profiling and bidding. Those are the two ones that I'm going to talk about, the lessons learned here. So first off, there's a massive variability in tool performance. So for example, here's a plot. Don't try to interpret it. All that you want to take away from this is it's kind of a mess, right? These lines are super squiggly, and there's a bunch of different error metrics here. There are a bunch of different tools around, and even at the phylum level, there's wildly different performance. Clark has a ton of false positives, whereas something like MetaPhyler has very few false positives, things along these lines. So it varies extremely widely. You can't just pull off a tool off the shelf and hope it works the best because they all have different performance characteristics. Beyond that, there's poor performance below the family level. Hopefully that goes away after this slide. But in any case, this one, we can try to interpret a little bit more. We have a whole bunch of tool names sitting around here. We got two metrics, recall and precision. And this is the family level, and this is at the genus level. This is for taxonomic profiling. And notice what happens, this area right here, just terrible at the genus level. So even though you see papers coming out all the time that says, you know, strain level profiling and everything like this, yes, in very specific cases, but in general, even performance at the genus level leaves a lot to be desired. Right? So beyond that, we can basically classify this into, there are three different kinds of methods. There are ones that are sensitive, things like Kraken and Clark and Bracken. There are things that are precise, things like metaflan, where they use marker gene or clade-specific marker gene approaches. And then there's ones that are actually good at getting that relative abundance. And so you can kind of see that if this table that was flashing all the time can now sit here, which is that across these different metrics of sensitivity, precision, and these metrics here measure how good we can reconstruct the relative abundance. You'll notice that the names are almost all distinct, right? Ones that are good down here don't show up as the best in the top, etc. So really, you got to think about what's my problem, which one of the tools do I want to use? Okay, but all this to say, those techniques that I've been talking about utilize a bunch of different approaches, either marker genes or k-mers or stuff like this, to try to get around the problem that the databases that we're trying to assign to are huge, and the input data that we have is also huge. So they're trying to do something, you know, fast to be able to get their results, because plain vanilla alignment, while we'd like to do that, is difficult with that data size. So I claim, though, that plain vanilla alignment, just take your database and align to it, is still good. So for example, if you got your reads, you got your reference database, you can just align straight to it, and then take care of all the different peculiarities of your mapping. So in particular, some of the reads map uniquely, and that's great. Some of the reads map in multiple different places, so you have to come up with some sort of probabilistic model that takes into consideration the sort of multi-mapping. And then after that, you can do some thresholding about, oh, what does the coverage across a genome look like? Am I only getting a bunch of reads on one gene? Well, that organism probably isn't present, probably some sort of horizontal gene transfer or something like this. And then you get your results. So if you want to take a look at this, you'll see that the performance of a method of plain vanilla alignment is actually much better than any of the other methods that I've talked about previously. But the reason why nobody does it is that it's extremely slow. Like on the order of 25 hours for 1 million reads to do this. And if you actually look at this carefully, you notice here it says viruses. That's because you need really small genomes to be able to make this sort of alignment approach work. So it would be nice to use this because all our methods vary quite a bit and there's no really good ones. And it'd be nice to use the workhorse of alignment. But the real problem is, besides being slow, it's also imprecise. The main obstacle is our data is too big, and the reference database is also too big to be able to do plain vanilla alignment. Yes?
Can I ask you, what if you don't trust your alignment? What if it's a lousy alignment?
Yeah, so in this process right here, like trying to do this workflow, you have to very carefully pick, what alignment are you going to do? what sort of alignment settings you want to say, yes, this really is
Okay.
an alignment, things like this. Yeah.
Right.
Yeah. So definitely.
I'm never happy.
Yeah, never happy. Yep. Cool. Okay, so even if you don't trust your aligner, sometimes it just won't finish in time, right? Because the database is way too large. So what can we do? So now we're going to turn our attention to the main sort of computational technique here to try to get around that problem. So in particular, containment MinHash. So the sort of problem statement is we got all these reads right here, short reads, a bunch of them. And then we have a reference database, all of our microbial genomes. And this is what I mean that there is a reference database is large. So back in February, when I pulled all the genomes from NCBI, that's how many microbial genomes I was able to get, about 265,000 of them. We got these strings right here. As a very first step, instead of trying to either do taxonomic profiling or something like this, what I might want to do is try to get a vector, a binary vector, indicating presence or absence of these different reference genomes in my data. So hence, a 1 right here means that microbial genome is represented in my reads. A 0 right here means that second one is not represented in my reads, etc. And if I could have a quick way to compute the presence and absence of these things, I might be able to hone down my database and just look at those entries of the database that are relevant to the exact data that I'm analyzing. So that's our goal. Well, are we going to do this in practice? To be able to do that, I'm going to abstract it a little bit. So the abstraction is going to use k-mers again. So strings of ACTG, length k. And if I form all the k-mers in all of my reads, I then get a big old set. So you can think of this just a set of k-mers. It's a very big set of k-mers, right? And this could be like billions to trillions of k-mers, depending on your k-mer size, how big and diverse your sample is, etc. And we have a reference database. I take each one of my genomes, I compute all the k-mers in each one of those, and I give that a name called some other set, like A1, and I do that for every single one of my reference genomes. All 265,000 of them. These sets over here are smaller, right? Because instead of talking about millions and billions of reads and all the k-mers in those, you just have a single genome, and you're counting the k-mers there. So you got a big set of k-mers, we got small sets of k-mers here. And then, instead of computing zeros and ones, the presence and absence of these, we could introduce a metric like Jacquard index to be able to measure the similarities between these sets. So Jacquard index, size of the overlap, or the size of the union, that is going to return a number between 0 and 1, indicating how much this big set is going to overlap with this one. Then I could also do it, how much does this set overlap with that guy. If the Jacquard index is 1, that means that these are completely identical, and you don't have a metagenome, you have just a single genome in your sample. If it's 0, that means they share no k-mers in common, therefore it's highly likely that this microbial genome is not represented in your reads. Jacquard index is cool, but it's kind of slow to compute. It's slow to compute because to compute this overlap right here, naively, what you have to do is you got to pick a k-mer here and say, does match the k-mer in here, pick another k-mer, and you got to iterate over all the k-mers in each one of these, enumerate the overlap. When you're talking about billions to trillions of k-mers, that can get intense, especially when you have hundreds of thousands of sets to test. You want each individual test to be rapid. So one way that we could rapidly compute Jacquard index is using this really cool technique called MinHash. Anybody heard of MinHash? No? Cool. Excellent. So let's talk about MinHash in brief. So this was introduced by a guy by the name of Andre Broder when he worked for AltaVista, the now defunct search engine. He was working on deduplicating web pages in their search engine. Very similar, in theory, kind of problem to be analyzing. But in brief, his idea was the following. We got a set, arbitrary set. In my setting, these are k-mers. What you can do is you can randomly sample these. You randomly sample them in a very special way, I'll talk about in just a minute. But I've randomly sampled and I've selected just the red k-mers right here. Randomly select some subset of them. And then you list all the ones that you sampled and you call that thing a sketch. It is basically a smaller or lower dimensional representation of this big old set. So it's kind of like a fingerprint. You're printing it by taking a random subset. And then, if you want to compute the Jaccard index with another set, you do the same thing. You randomly sample that guy, get all its lists of k-mers, and you call that guy another sketch. The really key sort of insight that Broder had is that if you do this random sampling in a very special way, such that the probability of selecting same k-mers, if they exist in the sample, is exactly equal to the Jaccard index. And he does this using these fancy families of minwise independent hash functions and minimizers on these things. And there's a couple pages of math to prove that it all works out. But basically, the probability that you're getting the same k-mers in each one of these sets is exactly equal to the Jaccard index. Therefore, to be able to estimate the Jaccard index, all you got to do is look at these guys and say, how much is in common between the two of them? So you go through the list, and you look, oh yeah, this k-mer right here is the same as that one. This one's not represented in this sample, so you take the red divided by the red plus blue, and there you go. This estimates your Jaccard index. And then you have some nice formulas that shows how the accuracy of this method depends on the sketch size and the original size, the Jaccard index that you're talking about, et cetera, et cetera. Question?
So when you're sampling, you're creating these sketches from your genome database, is that right?
Yeah, here the way I'm presenting it is just arbitrary sets. So I could do this with my sample, I could do this with my reference genomes, et cetera. In the setting that I was talking about, you'd probably want to treat this as your really big set, and then this is one of your reference genomes, right? Because we want the Jaccard index between those two.
This process of subsampling, is it always the same? So you could have these sketches kind of in your database, or do you use sample sketches?
So these can be computed offline once, and you can just store that. And they don't change because you're using the same sort of sampling functions. So every time you come across new data, all you have to hash is that new data. You don't have to go back and hash the database. Yep. Yeah.
So since we paused for a question anyway,
I'm
wondering about the k-mers and the k-mer lengths. When you're doing this, are you doing all this, let's say, with a set k-mer that is the same, or do you sort of iterate through?
Fantastic question. Yes. So we'll get later on to how we handle that. Okay. Yep. Great leading question. Okay. This sounds great. It doesn't really work for the problem that I'm trying to do. Why? Well, you remember that the big sample, it had billions to trillions of k-mers. And then our reference genome k-mer sets, they were on the order of maybe 1 million. And so I got one massive set, and I got one small set. When I take the size of the intersection over the size of the union, that union is going to include that big old massive set. So I'm going to be dividing by a huge number all the time. And in fact, the Jaccard index is always going to be really, really, really small. You then go stare at the formulas that Broder had, and you realize, oh, shoot, if I want to be 95% confident that I'm not off by more than 25% of the true Jaccard value, then I'm going to have to sample 10 to the 7th k-mers in here. Ugh. Now this suddenly becomes more computationally difficult to do. The more sketches or k-mers in your sketch, the more you're going to have to check each one of these guys to estimate the Jaccard index. So, it was a nice idea. It doesn't really work for our situation because we're dividing by that huge number from my sample. Well, so you might say, I might try to improve this. Jaccard index wasn't really what we wanted anyways for the problem. Indeed, if we think about it, this is the sample k-mers, and these are the k-mers from one of my reference genomes. All you really care about is how much of one of these reference genomes actually showed up in your sample. Who cares about the size of this thing? So in particular, what we really want is just to concentrate on this part right here. So that's just the containment index. Size of the overlap over the size of A. How much of the organism shows up in the sample relative to the size of the organism genome. So how might we do, does that work?
Well, in a sample, wouldn't you expect if the organism was there that the whole genome would be there?
Yeah, exactly. And so if this thing completely overlaps, then our containment index is 1,
Okay.
which is exactly what we wanted. Yep. And if they don't, it's 0.
And it's some relative.
Yes.
or if it's some fraction, then it's some relative of that order.
Yeah, exactly. So if it's 1/2, that means exactly half of that genome is represented in your sample. Yep. So how are we going to do this in practice? Just want to give you the basic idea and not run through all the technical details, but we want to estimate this thing again. So to estimate it, what we can do is we can stick this thing here into a big old Bloom filter. You may or may not have seen Bloom filters before, but basically it's just a data structure that allows you to very quickly ask, is this thing present or is it not? So I got a big old set right here, and I want to ask, oh, I have a Kamer. Does it belong to the set or does it not? It allows you to answer that question extremely rapidly. Yeah, as long as you're okay with every once in a while getting your answer incorrect. So I'm going to put my big old sample into one of these data structures where I can quickly ask, is a Kamer present or absent? Then after that, I'm going to do that random sampling and forming that sketch of one of my reference genomes here. So I randomly sample, I form one of the sketches, and then all I got to do is say, oh, take each one of these Kamers and ask, does it belong to my sample? If it does, fantastic. You got one of these points right here in the green region. Go to the next one. Well, is it in my sample? If not, oh, then you got one of these in the blue region right here. And you keep on doing that over and over and over and over again, and then you keep track of the ratios of those, and then your containment index is the number of successes or the number of ones that you tested over here. So basically what we're doing is we're enumerating the size of the little points in the screen area versus everything here. After that, you got to prove that it works. You can feel free to look at the details, but then we call it SMASH for Containment MinHash. I didn't. I was just talking about this on Twitter, and somebody said, you have to call this SMASH, which I think is a fantastic name, because I'm terrible at naming tools. So does it actually work in practice? How much of an improvement do we get by considering containment instead of Jacquard? So MASH, you might have heard of, is one of these methods based off the Jacquard index. And you can take a look, and you can see how your relative error changes as a function of how many Kamers you sampled, the number of hashes, the number of elements in your sketch. And of course, the number of samples that you have, each one of the method, the errors go down, right? Because we're making more samples, and we can better estimate the size of this area right here. But with this Containment MinHash approach, the error, it's kind of blown out of proportion because of this y-axis right here, but you can see that the error is significantly smaller. And the reason why that is if you're trying to do the Jacquard index, all these points are not helping you. So you need to sample a whole heck of a lot of them to be able to, by chance, end up in here. So, yeah, increased accuracy. And then you can do some cool things with this. So, for example, if you take a soil metagenome and you do this, you take a reference database, you form the sketches of all of those guys, and you ask, oh, what's the containment index of each one of my reference genomes to a particular sample? Then you take one of them whose containment index is large. Then you can pull out even really small things like tiny little viruses in a soil metagenome, because the containment index was large. So even though it's a tiny genome, we know, ooh, most of it is represented in my sample. And then you can go back and say, well, was it actually present? And then you spend a really arduous task of aligning that entire metagenome to that single viral genome. And then you get one of these sort of coverage plots that give you an idea of the viral reference genome over here and the number of reads that aligned in those windows. Where if this was buried in an entire alignment, it might be harder to pull out. You were able to detect it by using this approach right here. Yeah?
Is this also true when you want to assemble a bacterial genome? You see a lot of bacterial genome assemblies from metagenome data that you use for that.
Yeah, you could especially use this for reference-guided assembly, because this all is trying to fit to a database, right? So it can tell you presence and absence of things in your database. And then after that, you can do alignment and things like that. But it's not really going to be good at de novo. Yeah.
So what if I'm interested in an organism that is in a low abundance in the sample? Does this matter still?
Yeah, abundance here doesn't matter, actually, too much. It doesn't matter too much because these Kamer sets that we're forming, these are distinct Kamers. I don't care how many of them there are. I'm just distinct k-mers. Yeah. So if a k-mer shows up once, it can help you here. Yep. Yeah.
So once you identify those that are present, you then do you go to the next step where you would reduce your database?
You got it. Yep, exactly. So before we get to that, I'm going to get to Mariah's question, which is, what about the multiple k-mer sizes? And then I'll get to the database reduction. So if you've ever worked with Bloom filters, they're rather big, especially for metagenome data. And then if you change your mind about the k-mer size, you got to compute yourself another Bloom filter. And all of a sudden, you've got tons of Bloom filters sitting around. Each one is 500 gigs, over 10 different k-mer sizes. Now you're talking about 5 terabytes, over 1,000 samples. Yeah, that's not going to work. So if you change your mind about the k-mer size, you're kind of up a creek with this method. You got to do everything over again, which would be large or an arduous task, which is unfortunate because changing k-mer sizes is really informative. So here we have a plot of the containment index versus k-mer size. Each one of these lines right here represents the containment index at a specific k-mer size between my metagenome and one of my reference genomes right here. And then I do this for a different one of the reference genomes for another one of these lines. And then the overall shape of this plot, it kind of makes sense because, well, your sample has AC, T, and G. Your reference genome has AC, T, and G. They share exactly in common, so the containment index is 1. And then as you increase the k-mer size, you're basically getting more, you're increasing your specificity. And so even if we went way out here in a very large k-mer size, then we're basically at that point doing exact matching. Does this whole entire genome exactly show up in my sample? So it's not too surprising that the shape of this plot is going to be decreasing like this. But more importantly, you can get taxonomic information from this. So you might have noticed that I've colored this red for organisms that are of a different genus than something in my metagenome. And I've colored it black if the reference genome is the same genus as something in my sample. So you can see that if one of these reference genomes is distantly related from your metagenome, this curve drops off quickly. And if it's more closely related, it drops off more slowly. And if you look really closely, you can see a tiny little line right up there. That represents a reference genome that is basically the same strain as something in my metagenome. So seeing the shapes of these plots like this can be really informative. And I want to compute this. I don't want to have to, at each individual K, be creating some big old data structure to be able to do this. So how can we do that? A little bit of technical details here. What we're going to do is we're going to put each one of the sketches, remember which is the random sampling of the k-mers, into this data structure that allows me to look at prefixes real quick. So what do I mean by that? So for example, there's this thing called a ternary search tree. It's okay if you don't know what it is. It's basically all it does is allows me to very quickly look up, insert, and delete k-mers and all their prefixes, all in one go. So for example, a ternary search tree might look like this. Here's one where I've inserted words. I've inserted something, literally, someone, and somehow, and dog. And then you'll notice that it'd be pretty easy to look up all prefixes in here, right? So some is a prefix of all three of these guys, and it's really easy to look up, S-O-M-E. There we go. So the prefix has been stored in this thing as well. How am I going to use this? Well, my basic idea with SMASH, you take one of these reference genomes here, you form all of its k-mer sizes, or sorry, all of its k-mers, but now we're going to do it for a really big k-mer size, like 80 or 120, massive k-mer size. Then we're going to do random sampling, just like we did before. We get one of these sketches. Now with that sketch, I'm going to stick that thing in a ternary search tree. Why do I stick it in the ternary search tree? Because now I get all these prefixes stored in here too, and I can quickly look them up. Why is this helpful? Well, because these are k-mers for a smaller k-mer size, right? So I picked this large k-mer size. I now have access to that guy right there. And you can carefully characterize, if you randomly sample these large k-mers, then these prefixes are also a random sample of the shorter k-mer size. So importantly, these are random n-mers for some n size that's smaller. That kind of work? So now we got all of our k-mers in here from 1 up to whatever very large k-mer size that you picked in the beginning. And then what do we do with this? You repeat this for all your reference genomes. You take your next one, you form all of its k-mers, you randomly sample, and you stick it back into the very same ternary search tree as before. So what? Well, now we can use this in the following way. I've taken my reference database, I formed all these sketches, stuck all of them into the ternary search tree. Now when your sample comes along, you can stream this through your ternary search tree once. So you take the read that you have, and you say, oh, does this prefix show up anywhere in my ternary search tree? Does the next one? Does the next one? And the cool thing about this is it tells you not just if it showed up, but who it showed up in. At the same time, why is that important? Because then we get the containment indexes for all values from k equals 1 to whatever big K that you did, all in one go. Notice no bloom filters, nothing big to compute here. Sketches are small, right? Because they're little subsamplings. I don't have to do anything with my data. I just stream it through once. Pretty lightweight method.
David, sorry. So then what's in your tree is the thing you called n-mers?
Yeah, in my tree are my sampled k-mers
Right.
and all of their prefixes.
Okay, so the whole. Okay.
Yep. Yeah, and so using those prefixes allows me to compute the smaller containment indices all the way up to whatever large k-mer size that I picked. Great. So what do we get from this? We basically are able to recapitulate these containment index curves like this, just like the plot beforehand. And we don't have to compute it at every single one of the values here. We just get all of them boop, in one go. Fantastic. So is it actually useful? Now I can get to the database filtering question here, which is we package together into a technique that's currently being submitted, and we call it meta-line. The whole idea here is you take that big old reference database, all 265,000 genomes. I think it was like 787 gigs when I downloaded it all. I'm going to make all the sketches of these guys, put it into that ternary search tree, yada, yada. Then I'm going to take my reads, stream it through that ternary search tree, compute all the containment indexes, use that smash approach that I talked about. And this is going to give me, for every single one of my reference databases, or database entries, a number that tells me how much it overlaps into my sample. You pick some threshold, say I only want to consider ones that are above 0.8, and then you've been able to reduce your database down to just those entries that highly overlap with your sample. And these numbers right here are not made up. So it took an ocean sample from the Terra Ocean project, and this is a realistic size in the database reduction. This is orders of magnitude smaller. Because of that, you can actually go back to just the plain vanilla alignment approach. And then hook it up with that whole same uniquely quantifying multi-mapped reads and probabilist, yada, 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 quantifying these guys, filtering the results, and you get the results. Previously, going from here straight to the alignment, way too computationally difficult. But this is only good if it actually works in practice. Does it actually speed things up, and how accurate is this? So let's look at a few results. Results of this basic workflow right here. So I'm going to use that CAMI simulated data. I think it's important to say that because I didn't make that simulated data, so I'm not trying to rig anything here. And these are basically 8 different data sets that vary in complexity and model different environments and stuff like this. So, and then I'm going to evaluate them using this recently published sort of benchmarking suite at a particular genus rank. So let's look at one of these precision recall plots right here. So I got precision on the x-axis, I got recall on the y-axis right here, and I got a whole bunch of methods that try to go from reads to one of these profiles right here. And you might notice Metaline, its default setting sits up here. We got sensitive and precise settings depending on how you fiddle with your alignment parameters and your cutoff things and all this kind of stuff. And then the rest of the tools are down here. So when I said plain vanilla alignment is good, that's what I mean.
So David, can I ask you a question?
Yeah.
It seems like the initial sampling of your reference databases, sort of random sampling, is
Yes.
a bit of a random aspect, but an important one.
Mhm.
Is that something that matters a lot, or is it such that the later steps kind of make up for, let's say, something that didn't happen to get randomly subsampled into your library because there's this sort of wiggle, let's just call it that, and the alignment such that you'll pick it up as something that way back.
Yeah, so it is important in as much that whatever random sampling function that you use, which we refer to as a hash function, has some desirable properties. And so that it's close to uniformly randomly sampling. And computer scientists spend a lot of time trying to design functions that get close enough to uniformly randomly sampling. So what I did here is I just looked up and said, oh, well, this one looks like it has good performance characteristics, pulled it off the shelf, make that decision, and never look back.
Yeah, so someone else has optimized that part,
Yep.
and it's something that you could change in the future, but as long as it's working well enough, it's fine.
Yes, exactly.
All right.
Other metrics, for instance, like looking at the F1 score here again, sort of the balance between precision and recall. Results speak for themselves. Other metrics like Jacquard index, unifrac error, stuff like this. So relative abundance ones, you can see that's Metaline as well. The lighter colors are better on this particular scale, either the sensitive or the precise. Over a bunch of different metrics, no matter which way you slice it. This alignment is good. Woo. Oh, great, another table flash. There we go. Next, we looked at a mock community instead. So let's move away from simulated data. We'll look at a mock community. And here again, if you look across a bunch of different metrics right here, Metaline in either its default or precise settings, the bold really does not show up on this screen. So you can't really see, but it's best in all of these, etc. So it works in mock communities as well. And that way, when we go to something like a real-world data, we can have some confidence that the results that we're getting really are present. And what about speed? So, boy, howdy, that's annoying. Does this database reduction actually help things a whole lot? So here I'm comparing this Metaline approach with database reduction and just the naive alignment, which is just align directly to the database and worry about stuff later. Let's say I have a massive supercomputer to be able to do this. Well, the runtime is a few orders of magnitude smaller after we do the database reduction, which isn't too surprising. But the more surprising thing is that the false positive rate also goes way down. Because with this pre-filtering step here, you've already excluded these organisms that could hamper your downstream analysis of trying to deal with multi-mapped reads and stuff like this. So only looking at ones that are highly similar globally reduces your false positive rate by a couple more magnitudes. Guess what? So then we get to real data, like the Terra Ocean project that I was talking about. The speed in general is competitive with these sort of pure K-based techniques that are like super implemented in C and everything like that. And I'm using a plain vanilla Python implementation here, and it's still competitive. But the most important thing is that the results that you get are more biologically realistic. We have no ground truth here, but we have other studies who have studied the different samples. And we can look at, for example, eukaryotes. Metaflam reports a single one. Kraken reports Homo sapiens as being present in this ocean sample. And then this Metaline detects some organisms that are supported by other studies. And so, hey, on this real data, it's returning things that we would kind of expect because it's supported by other studies. Indeed, when you move to prokaryotes, then very detailed studies have looked at the abundance of these guys with a bunch of different methods. and find that this is what their abundance distribution should look like. And indeed, Metaline is the only one that recapitulates the relationships between these guys. So probably works on real world data as well. Now, very last bit, a couple slides on, you may have noticed that I snuck in right here a little, oh, you set a threshold. And you select everything below that. How the heck do you select that threshold? Is a similarity of 0.8 good? Maybe you need 0.95, maybe 0.2, I don't know. So I want to relate it to some quantity that I do have some intuition about, in particular, average nucleotide identity. So I have these plots, K-mer size versus containment index right here. Right now, yeah, I can see that they're all different shapes. All I know about them are their different genomes right here. So what I'd like to do is to be able to predict relatedness from these curves. If I see a line that looks like this, how related is genome 1 actually to my metagenome? And everything else in between as well. To be able to do that, I'm going to have to model this thing. So I'm going to assume that your genome is actually present in the metagenome, and I'm going to ask, if it's present, what would the curve look like? At a certain, if it's related at a certain distance. So how related is a reference genome to the metagenome? So we're going to stick that up on the side. I'm going to use a probabilistic model, a very simple model of evolution, just a site-wise Bernoulli process. So I'm going to take my genome, I'm going to look at each nucleotide independently, take a biased coin, flip it. If it's heads, I leave it alone. If it's tails, then I change it to something else. How much my coin is biased is that mutation rate P, which is exactly the average nucleotide identity under this particular model right here. So that's the model that I'm going to do, and I'm going to spend way too much time making calculations and proving things, and I get big ugly formulas like this. Don't try to parse this. There's just one big takeaway here, which is it allows me to compute the expected containment index over a range of K-mer values. And then I got a formula. Critically, this formula on the right-hand side, my metagenome M doesn't show up anywhere over here. There's no M's in this guy. And that's actually nice, because that means I can predict the shapes of these curves based only on my reference database, not on my data, right? Because I'm just trying to figure out what these shapes would look like if they showed up in a sample. So I don't care about the sample. All I need is my reference database. So I can compute this once. You give me new data, I don't have to do anything else, I can just check. Then, what I can do is the following. I take this guy back, I can solve the inverse problem. Hey, my curve actually looks like this. What was the p-value? And that allows me to take this legend here and now change it with average nucleotide identity. And here, that allows you to then say, well, if I want my threshold, I'm only interested in species. And I think that anything 95% ANI or above is going to be a species. And then you check, okay, here's the containment index that you're going to have to use to be able to do your cutoff, and then you can do your database reduction, your alignment, yada, 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 stuff like this. So it's pretty cool to be able to relate this or figure out how related these reference genomes are to the metagenome, and it gives you a great way to threshold. Awesome. We'll have time for questions. So, in conclusion, what am I trying to do with all this stuff? My personal goal is to try to drill down on the unknown unknowns of our data. So from these input reads, using all this fancy smash and alignment and metaline stuff, I basically want to be able to partition my reads. Partition those reads that are of known origin, which I can define as something closely related to something I've seen before. And then I also have reads of unknown origin, things that are distantly related to anything that I've seen before. And then whether you like the term or not, this is oftentimes referred to as microbial dark matter. And personally, I think that's where all the cool stuff lives, right? Because who knows what's in there? You feel a little bit more exploratory. And what might happen if you were able to disentangle these, reduce your data significantly more, assembly might become a lot easier because you've sort of taken out all the stuff that you already know who it belongs to, and you're not really interested in that, and you can just drill down on the unknowns of the data. So, in conclusion, this whole method allows you to quickly compute containment index, Jacquard index, in a fast fashion. Lets you do multiple camera sizes in one fell swoop. And it facilitates these sort of meta-line database reduction approaches. And then you can relate it to this average nucleotide identity for quick cutoff estimation or intelligent ones. If you're interested in the theory behind this, there's a GitHub page with the entire paper that's reproducible. So you can go in there, change a few numbers, recompile it, see how the figures change, stuff like that. Nobody cared about that, and I spent way too much time doing it, but it was fun. Then just the smash method, which does the containment index in one go. That's contained in this GitHub repository. And then if you want that whole pipeline of doing, take the database, do the database reduction, do the alignment, do the multi-mapping reads, all this kind of stuff, that's contained in this GitHub repository right here. So, I'll wait till people finish taking pictures. There we go. Nothing is done in isolation, so I'd like to acknowledge collaborators, Sergey Mangul, longtime collaborator of mine who just got an assistant professor position at USC. He was a former postdoc of Eleazar Eskin at UCLA, and along with one of Eleazar's grad students, Nathan. He's also at UCLA. I met all these individuals at the CGSI, Computational Genomics Summer Institute, that I helped to run. If you're interested in spending summer in beautiful Los Angeles on the UCLA campus, feel free to come and talk to me. I can point you out to the resources, and oftentimes there's some sort of funding available for travel or things like this. One of my former PhD students, Human, who is now at Simon Fraser, helped with the theory behind SMASH. And I'm told I have to say that portions of this award were funded by National Science Foundation. Yeah, so thanks for your attention. Questions? Yeah.
I don't think it was useless that you make the paper I think. Have you picked the data set from that Platypus conquistador paper and run through your pipeline?
No, what is it? The platypus?
A paper a paper that came out and said, oh, we have anthrax and platypus and all this stuff on the
Oh, was this the subway?
Yeah.
Yes,
and
yes,
then
yes.
they came and reanalyzed the data with like more stringent. Have you had the chance to get that? That would be a really cool data set.
That would be, I'm pretty highly confident that it wouldn't show up. I should definitely check that though. But yeah, one thing that I did do with that is I reran Metaflan because that's what they were using. And it was ridiculous the amount of support. It was like one single read that was loosely mapped to one single, and I'm like, okay. But yeah, that'd be interesting to do.
I think with the anthrax, it would really depend on what nanny product you use because they're so clonal. So if you use a species product, you would likely get that false positive.
Yeah, and we would have to see if the uniquely mapped reads versus multi-mapped reads would help us distinguish between those. Because you're right, just doing the Containment MinHash stuff, you might say, well, all of them are somewhat similarly related. Maybe after the alignment, you can disambiguate it, but yeah, I would have to see.
So I wonder if something like that would be an interesting microbiome project. So for dog and cats to get together and maybe take a data set like that and do some things with it. I'll just throw that out there as because we have a lot of expertise like that you would be able to say, if this cut off, you won't be able to look at anthrax in the way that you might. And there might be other things that we could do things with because of the expertise we have.
I have a question. I know who dog is, but I have no idea who cat is.
Yes, cats is still in the process of being formed. So I've been.
He's one of the cats.
I'll start cats.
Start the cats. So cats is
computation, algorithms, theory, and statistics. And yeah, to go with the dog. And
We had our first meeting yesterday.
yes, all two of us.
Yep. Make sure they don't fight. We put the head dog and the head cat.
Exactly. Yeah. So we're. I'll probably be emailing some of you to gauge interest and maybe have a roundtable discussion. I have ideas about how it can look, but I'd like to also include you guys in figuring out what the best way would be to bring together for our communal usage.
Would you be interested in giving a workshop?
Yeah, sure.
You would be hired.
Yeah, okay. Cool.
I think everybody's thinking about all the projects that, gee, I need to talk to David to see if he can.
That's a question, maybe.
Yeah.
When you're doing the database production, so like just this theoretical situation came to me where you don't have, so you're trying to do your cutoffs at the species level, but then you have something in your metagenome where it is only matching to something that's at the genus level in your reference database. Yep. So then you would screen that match out because it was only at the genus level, right? So you don't see that.
Yep.
Is there a way to do it that it doesn't make it way too computationally expensive to find things that match at the species level, but if you don't, then you can go back to
Totally. That's exactly how you do it, the top down.
Yeah.
Right. So you would start at a containment index of 1, and then you would say, oh, nothing is related there. Reduce that slightly. What did I get? Oh, awesome. Next level. Take, don't include those ones that you've already done at the species level. Keep on doing that like that. Yep. Yeah, that functionality is not in here. You'd have to sort of manually do it.
Yeah.
But that'd be a cool feature. Yeah.
I just have a quick question about the sort of data structure of the sketches, which is maybe more about a hash than about a containment part, but
Sure.
I'll be able to give you a quick answer, which is that I'm curious when the sketch is made, the way that you described it, is it such that if there are, let's say, precise duplicates among the k-mers that are picked, that they're left in place because they represent abundance, or is there some other way that that is encoded in the data?
Yeah.
So the sketch is never containing a duplicate.
Yeah, the sketches never contain duplicates because it's just looking at distinct k-mers, not looking at abundance, which is why the only thing that I can compute is presence and absence, not relative abundance, and I leave that part to the alignment.
Yeah, okay.
Yeah.
So that's
Yep. Cool. Thanks.